for you. Okay, so last class, we talked about gears, if you remember, and we had a facile learning assignment on gears. First and foremost, do you have any questions about that, about gears? No? Oh, we have a question here. Oh, you're here with Victoria. Hi, Elizabeth. Okay. Okay. Actually, speaking about facile learning here, I'm going to turn it on. Just give me a second. Facile learning. There is one assignment I forgot to put in the beginning of quarantine. It's Unit 1, Lesson 8. It was on balancing equations. So I put it on Schoology already. But if you didn't do it, you might want to review Unit 1, Lesson 8. Okay? Okay, so let me share the screen now. Share the screen. There we go. So the homework of last week, when it comes to Unit, Unit 13, it was Lesson 4 on gears and that sort of thing. So were there any questions about this? It's actually a little more advanced than you needed. I hope it wasn't too difficult. Any questions? You can stop me. Take a look. Like this one, number 5. Let's see if you guys understood this. Gear 3. Gear 3. Does it turn faster than gear 4? Does it turn slower than gear 2? Does it turn slower than gear 1? Or does it turn slower than gear 4? So we can start by saying gear 3 and 4 are the same size, so they will have the same speed. So this doesn't work, this last one here. Turn slower than gear 1. So gear 3 is bigger than gear 1. So yeah, let's see if that's a possibility. Turn slower than gear 2. No, it's smaller than gear 2. So it should be faster. And turns faster than gear 4. No, they're equal. So the answer to that one was turn slower than gear 1. Any questions about that? Because in grade 9, it's really just about recognizing the gears. Are they going slower or faster? That's it. Okay. Yes.
Which one is it again? It's Unit 1, Lesson 8, right?
The extra one?
Yeah.
The one I forgot to add?
Yeah.
Yes. Unit 1, Lesson 8.
All right.
Yeah. It's on chemistry, though. Okay. Okay, let's hear. You see, everybody see the image on the screen? Oh, it's the same one as this one. Okay, right here. Who can tell me which gear will go the fastest? Can you put your answer on the chat? Let's see. Which gear will go the fastest? Yes. Excellent. All right. Then which one will go the slowest? Let's see. Let's see your answers. Like a rain of answers. Yes, very good. Number 2. I think you guys got that. Very good. So let's see if I have a question from an old exam. Hold on. Where have I got you? If you can see this image. Okay, everybody see the image on the screen? So who can tell me just by looking, just by the looks of it, is this going to speed or slow down or the same? The speed, will it be the same, slow down, or up? So we're looking at component 1 is the driven gear. Because look, component 2 is the driver. This is the one that's attached to the handle. So let's see. What do you guys think? Same, yeah, same. I know it's not very clear, but usually they would give you number of teeth. But just by eyeballing the size, they look like they're the same. So it would just keep the same speed as your hand. So if you're the driver, if you're going really fast, then the driven gear will also go really fast. That's good. Same size. What else do I have image-wise here? This applies to this too. All right. So you have a gear attached to the pedals of the bicycle and a gear in the back. First question, which of these two is the driver gear? The driver gear. Which of these two is a driver gear? The one with the pedal or the one in the back? Let's see your answers. Yes. Very good. The pedal is the driver. Okay, thank you. Everybody's answering. That's wonderful. Okay, so question for you. Now, the way it's placed like this, okay, will this be going fast or slow or the same? Let's see. Yes, faster. Excellent. Because the driven gear is smaller. Yes. You guys are fantastic. Cool. Okay. So this brings us to, so I'm going to stop the facile learning. You guys should be okay right now. If you still have issues with that, I'll have a tutorial soon on engineering if you feel that you still need help with gears. Sounds good? So the next part is the review. If we take it back all the way to the beginning of the year, when we did microscopes, if you remember that, we had a sheet on microscopes. And in my blue notebook, I am on page right now, page 83. So if you remember, the beginning feels like ages ago. We had to discuss what engineers do when it comes to drawing technical diagrams. There are specific lines that it's a language that all engineers use, and architects, I should say, when they draw. Here, I'll share the image again. 1 second. When they draw things that are as complicated as a smartphone, there's a lot of stuff that goes on behind the scenes of a smartphone. I'll show you what I mean. Techno, I just had it open, but of course things disappear. Where is it? Where are you? Bear with me, bear with me. Oh, nope. Where's the phone? Right here. The wizard is here. Where are you? I'll just type in phone. Should be easier. So forget the phone. I will go with, we just do extra large. There we go. Oh, sorry guys, I just had it. Oh, there it is. There we are. There we go. Remember this image, people? We looked at this in the beginning of the year, how it looks really complex. This is an actual tech diagram for designing an iPhone. and decided to crash on me. There we go. There we go. So not to complicate your lives, but this detail is so important. That's why your iPhones are so perfect, and everything fits properly in its proper place. And then you have all the views. You have a side view, front view, the other side, and the rear view, the back view. And then you have all these lines. And this is what, if you remember, we had all these lines that we looked at. And would you imagine the sizes, if they didn't have these arrows and these lines, we would be totally lost. It would be just a bunch of numbers, if you remember this, right? So who can remember, first of all, let's say this number here, 51.70. Is this in millimeters or centimeters? Generally speaking, units are they in millimeters or in centimeters? Let's see. Let's see your answer. Millimeters, yes. Bravo, thank you. Yes. So let's see what, if you remember, this is a while back, but it is a review. These arrows, are they dimension lines or extension lines? Which one is it? Dimension or extension? Yes, dimension line. The word kinds, it tells you. This is where the dimension is written. So all over the place inside the image of the iPhone, you have all these numbers that show you the size of whatever object, whatever thing that you're representing. Like here you see, because it's so small, the slit on the side, I guess it's the power button. Yeah, the power button. Yes. Because it's so small, the arrows are drawn on the outside. Okay. But what are those long lines called again? See, I'm pointing at the long lines that are with that always go with the dimension line. They're over here also. I'm pointing at it. Let's see. Yes, extension. Very good. Okay. So that was, let me see if I have the notes handy. So whether it's an iPhone, design of an iPhone, or design of the Champlain Bridge, or anything, really, there is so much that goes on, even like your mug, everything that goes on, there is some kind of design before it is being manufactured, okay? Bear with me 1 second. Okay. Anyone missing the notes of this page 83? I can pull it out. Anybody need the notes of 83? This is a time to tell me. Okay. Yeah, they're all, by the way, on Schoology. So if ever you're missing anything, I put them all in one lump, like one whole engineering notes. Okay. The next thing was projections. Projections, we had isometric, we had oblique, and we had multi-view. So multi-view is what you did in the past few years. Okay, let me see if I have an image to show you. 1 second. All right, let me just share that with you. So notice here the difference between the isometric drawing on the right, where notice here I'm pointing, you see it's like it's standing on a tippy toe. That was the trick I was giving in class, is as if it's a corner. You see the corner, and then they project on both sides equally, both same angle. Iso for equal, metric, equal measurement of angle right here. Okay. Whereas here, this is what you're more used to drawing, like in grade 8, grade 7, when you were drawing multi-view projections. They were like in 2D, and depending on the view, whether you're looking side view, front view, top view, that sort of thing, okay? What else? So that was the projections. Please stop me if you have any questions. If we move on to the scale reduction. Wait, was there something after this? Let's see. Second. Oh, this actually, before I move on to the scale, I forgot to show you about the oblique. Remember that oblique, you have an entire face in the front, and only one side is on the right, like, or the left, projected on the right or the left. Whereas in isometric, both sides are projected. You can actually see both sides, okay? But oblique, it really says it oblique as in a diagonal. Okay? Stop me if you have questions. This is really just a quick review before we do the Kahoot. Okay. Okay, next. This, by the way, I am right now on page 86. Any of you missing anything on page 86? This you can tell me now.
Yes, I'll have something on 86.
You're missing, or you don't have, or you have?
No, I don't have the notes. Like, I haven't wrote it down.
Mateo, you don't have it?
No, I didn't write down the notes.
Ah, okay. Okay. Are you missing 86? Mateo?
The page or the notes? Because I'm missing the notes. I have the page.
The notes, page 86.
Yeah, I didn't write them down.
Ah, okay. Okay, 1 second. So I'm going to show you something that will be useful in case we speed up and you didn't have time to finish. Just look at the screen. In the materials, when you go to materials on Schoology, and you go engineering chapters 11 to 12, click there, and they're all here. Look, all tech notes.
Okay.
Okay, so I'll show you. You're missing page 86.
The other way.
Should be there.
Thank you, Miss.
You
I'll
see?
check that out later. Thank you.
Right here. Hold on, right here. You see that?
Yeah.
So, I just want to remind you guys, when we do a scale, when we draw something to scale, the first number, and this is what I need you to highlight on page 86, the first number on the left over here, number 1, is the length of the drawing. And then the second number is the length of the actual object. Okay, so on the left, it's the image. On the 2 is the actual object. So that's why it makes sense. Look here for scale reduction, 1 being the smallest number on the left, and 25 is the actual object. So the way to read this would be like the image is 25 times smaller than the actual object. Okay, and then 1 to 1 is the same size, but then here scale increase, the image is 25 times bigger or larger than the object. Okay, who can tell me in what situation would I need to draw this, use this particular scale, a scale increase? Can someone give me an example where I would need a scale increase? What kind of drawing, what am I drawing if I'm doing a scale increase? Let me hear those answers. You can unmute yourself or put in the chat. Let's see. A computer chip. Ah, yeah. Something small. But a paper clip. Yeah. But you know what I'll say? When you guys draw on the microscope, when you draw something, you notice you write like 100, 400, even 1,000, I believe, or 4,000. So, oh no, sorry, it's 10. Sorry, rewind. It's 40, 10, 40, 100. And there's 400 also. So every time you're like multiplying, you're increasing the size of the object, which is in this situation would be a cell. If 400, for example, the largest one on a microscope, would mean that you're multiplying by 400 the actual size of the cell. Okay? So that would be on 86. Above it, we had this exploded view, if you remember. Why would I need to do an exploded view? Anybody would like to? Unmute, please. Or write, why would I need to do an exploded view? How is that useful? Anybody? To see the attachment to understand how the pieces fit into each other. Yes, very good. And it's very useful when we're putting together like, you know, IKEA things, or here, let's see. Let's see if I can get you the exploded view. Yep. I'm going to share the screen with you. Oh, right here. All these are exploded views, and it looks really complicated, but obviously you probably have simpler objects to put together. But for like mechanics or other technicians, they really rely on the exploded view to be able to assemble things. Okay? Like that's inside of a lock. You see that? See how the exploded view really details what goes in first. Okay? So you would need that if you're assembling something, whether it's as simple as, let's say, drawers, or here like that, like a lock, how to insert the lock. Okay. C'est bon? Okay, the next on the list was page 87, diameter, radius, and angle. So that I have seen. I'm gonna go back to the image of the iPhone right here. So can you see? We have three symbols: diameter, radius, and angle. And I have that. Where is it? Where is it? Where is it? Where is it? Oh, right here. Do you see that? You have the circle with the line across. So this is your diameter. And you have 14.6 is the size. So the diameter of the button is 14.6. And look at your phone. If you have a button, because mine doesn't have a button, but if you have a button, it is about that, 14 millimeters. Okay. All of this, avoid this writing over and over and over diameter, because as you see, the image is already jam-packed with information as it is. So if you keep on writing diameter, diameter everywhere, it just makes it even more packed and harder to read. Okay. So the more symbols we use, the better. What else? We have another one, the radius. Let's see if it's in here. I did see it somewhere. Just one second. Oh, I think it's this one. So this would be, I think it's the jack on the bottom where you plug in the charger, right? So you have R for radius. So that would be the radius of this particular curve. Like it's so detailed, even the curve that's on the left side and the right side. That's why they wrote 2 times, because it's both sides. And you have the radius of this half moon, it's so detailed, is 3.4 millimeters. See that? And it's times 2 because you have 2 sides. That's for R. And let's see, where do I have an angle? Angle, where are you? Angle, I did see it. Be patient. Oh, right here. All right, right here. Notice how we're looking at the proximity of, it's called proximity cone. So I'm assuming this is for the camera. Is it the camera? It says 90 degrees. So you have like an arrow. Usually it's double head like this, and it's at an angle. It's like curved because it's part of an angle, like part of a circle. As opposed to the dimension line is straight, like that. The angle is a curved double arrow. Okay. So far, if you get this section, can you put a 5? If you understand, a 3 so-so. And anything I need to repeat. Okay. Next is page 87, tolerance. And that, I'm gonna try and get you an actual question. Okay. Where is it? Close that. Oh, no, you didn't see that? Okay. I think I closed. I closed my my notes, so I'm gonna open it again. Page 87. I'm gonna go to my materials, engineering, all tech, page 87. Okay. I was at here. Everybody have page 87? So tolerance, we talked about it briefly. I think during one class, we had one where we were talking about when we were drilling, if you remember the drilling of the cap for when we were doing the respiratory system. We had to drill a hole in the cap, and then it had to be big enough to fit the straw, okay? If you remember, before doing this, I had to pick the proper drill bit to make sure that the straw can fit, but not be too wobbly either. Okay? So there's like a leniency of how much I can play around with the size of the hole. It cannot be too big and it cannot be too small, okay? If the hole is too small, then the straw wouldn't have fit. So that's why we call it a maximum variation. There's from very small to very big. You see, it says, if the tolerance is not met, then the object will not work. So usually you see again that symbol, the diameter, and it says 10, and the way to say it is give or take 2, okay? And 10, so 10 plus or minus 2. Literally, you do 10 plus 2 is 12, then 10 minus 2 is 8. And we do that to know the maximum variation of the hole, okay? And this was for a test tube rack, I believe. Yeah, test tube rack. To be able to know what size test tube I can place in the hole, right? So you have some test tubes that are, let's say, 13 millimeters wide. Will they fit in the hole? What do you think? If the test tube is 13 millimeters wide, will they fit? Let's see your answers. If the test tube is 13 millimeters wide, will it fit? No. Exactly. Exactly. So You can also say, well, let's say the test tube is 7 millimeters. Look, it could fit, but it's going to fall, right? So for this test tube rack to be functional, for the test tube not to fall, well, that's the whole point. You want the rack so that the test tube sits securely into it without falling. So if you have a really small test tube, smaller than 8, yeah, it will go through, but it will fall, okay? And then everything that's inside will fall out, or the test tube itself can break. So basically, for us to have a secure test tube rack where nothing would fall, the proper dimensions are anywhere between 8 millimeters and 12 millimeters, okay? So let's do, I just want to show you one example from an old exam, because yes, it's easy to understand now, but when you read the question, sometimes the way they twist the question around is not as straightforward as this. So just give me a second. I will find a good questions on that. I believe in your, okay, hold on, I'll show you. Hold on. Back to Schoology, if you notice, I have in my materials in the June 8th week, this week, I put an exam, a June 2018 exam, part C. Okay, and it was about an oscillating fan. I'm gonna skip to the tolerance question. That one. Here it is. Okay. Everybody bear with me here. I am on page number 25. This is already in your Schoology. You can print it whenever you want. 25 says, when manufacturing the fan, the appropriate size screw must be made in order to fit into the drill hole in the housing unit of the fan blades. Okay. The rear section of the housing unit, as observed from the front of the fan, is illustrated below. So they give you the housing unit and the screws are here. See these screws? And then they even give you the diameter. It says here, wait a second. The appropriate size screw must be made in order to fit into the drill hole in the housing unit. So these circles are actually the holes, okay? And that symbol again comes back. What's that symbol again? The diameter, yes. So the diameter of the hole is 4.1, give or take 0.2. Okay? Right away, guys, when you see this, plus or minus, right away, do the math. What's 4.1 plus 0.2? Oh, 4.3. Yeah, let's see. Yeah. And what's 4.1 minus 0.2? Let's see your answers. Yes. Right. You need that. As soon as you see this, guys, right away, you have to do the math. So you know the range, okay? So now, the table below provides information on dimension and tolerance for 4 screws. So I want to choose a screw that would fit properly anywhere between 3.9 and 4.3. Okay? That's the size of the hole. So let's see. So now you have the screw. It says the table below provides information on dimension and tolerance of 4 screws. So let's just do the math here for the screws. So now I know my hole. The hole size is anywhere between 3.9 and 4.3. And I have to pick a screw that could fit in there properly. So I'm going to give you a minute, guys. Take a minute and figure out. You need a pen and paper for that. For the screws, 1, 2, 3, 4, the dimension of the screws. I'm going to take a minute and do that too. So screw 1 says 3.2, give or take 0.8. So the size of this screw is anywhere between, I'll give you time to do it, 3.2 minus 0.8 is 2.4, and 3.2 plus 0.8 is 4. So screw number 1 is small, too small. It has to completely fit the entire thing, not just sometimes. Okay? Okay, I'll give you a minute. Continue doing what I'm doing. 3.4, give or take 0.6, means 3.4 minus 0.6. .7 minus 0.1, 2.6. Is it 2? 1 second, Michael, I'm not finished doing it. 3.5, 3.6, 3.8. One second. Oops. Okay. Oh, wait, there's something we didn't read here. Which screws should the manufacturer use to attach the housing unit? Screws with a diameter of less than 3.4 will not function. Aha. So Michael, no, that doesn't work. Screws with a diameter of less than 3.4 will not function. Okay, what about screw number 4? .9 minus 0.5 is 3.4. And 3.9 is too big. So I'll give you a minute. Think this through. Any questions? People not understanding the subject? I mean this this question.
I have a question.
Yes, go ahead.
So pretty much the way to figure this out is that the tolerance, like the maximum tolerance, has to match that of the original dimension.
Yeah,
Like
but careful what you're looking for. Okay, so for example, it is a hole, right? I need something with a hole in it. Okay, so this hole, okay, has to be able to be big enough to fit the screw. Okay, it's like, I have to get one. Wait a second. One second. I think I have something that could work here. Oh yeah. Okay, bear with me here, guys. Everybody look here. My you see this? The holes here, they have to be big enough to fit the screw. So this is the screw that I fit in here. Okay? So the hole has to be slightly bigger. Makes sense, right? If the hole is smaller, I can't fit this in. Forget it. I won't be able to fit it. So the hole, the same with us when we did the drilling for the straw. The drill had to be slightly bigger than the straw. Otherwise, the straw won't fit. Okay? That's the same idea. So in the question, we're asking you, which screw would be slightly smaller, basically. I'm just retranslating it. Would be slightly smaller than the whole to fit. And to be snug too. Like you don't want it to be too wobbly either. Got it? You have to be careful with the question, what they ask you. So we'll go back to the question. Any verdict on the answer? Any verdict? Rachel, what do you think? Is it tricky?
Well, the thing is that like I had an answer, but I did it wrong, so I don't know if it's right.
Okay.
I thought you figured it out another way.
All right, I'm gonna share what I'm gonna do here. Hold on. Anyone else have a verdict of an answer? Let's hear it before I give the answer away. Well, anybody? Anybody? Isabel? Nathaniel? You guys are awfully quiet.
I think it's 3.
I think so too. Yes. Okay. Here's what I wrote. First, I figured out the size of the hole. The hole, it says it's 4.1 plus or minus, give or take, plus or minus 0.2, which meant the size of the hole is anywhere between 3.9 and 4.3. That's the size of the hole. Okay? Then it said the 4 screws. I have 4 screws. Screw number 1, the range is 2.4 to 4. Okay. Screw number 2, the range is 2.8 to 4. Screw number 3 is the range is 3.6 to 3.8. And the screw number 4, the range is 3.4 to 4.4. Okay. So in the question, it said that anything below 3.4, it will not function. Okay, you see here? I should just share the screen. It will be easier to go back and forth. You see? It says here, screws with a diameter of less than 3.4 millimeters will not function. So already I can eliminate the first 2. Okay. What else? Then I'm here. I have, there's 2 possibilities, 3 or 4. It says 3.4, like this one here, 3.4 to 4.4 doesn't work. Why? The hole stops at 4.3. How can I have a screw larger than the hole? It will not fit. It will get jammed. Okay? So 3 works the best. Wait, that was a terrible circle. Hold on. 3 works the best because number 1, it is higher than 3.4, and number 2, it still is slightly smaller than the hole. It has to be tight, a little bit smaller to fit the hole. Okay, so if it seems a little like vague, I'm gonna give more questions you can practice. So on that note, would you like another question now, or I'll give it to you for homework and you work on it? Can you put your answer on the chat? And I go with what you guys want. You want? Go ahead. Or do we move on? Okay, how about we go with the 5 and a 3? 5 if you understand this question now, after I explained it, or a 3 if you're still not getting the hang of it. Okay. Sounds good. So then we can go ahead and do a short Kahoot before, what time is it? 1:50? Okay. Because I did not make a Kahoot for electric engineering. So before I move on to the Kahoot, are any of you missing anything when it comes to tech, the engineering stuff? Take a look at your notes. Anything you want me to review, go ahead. Tell me now. Like electric engineering, for example, is on page 102. Before I do the Kahoot. Unfortunately, there's no facile learning on electric engineering. So maybe I can share a question with you that I saw, like an old exam question, the 2019 exam question. 1 second. I have access to the exams. Just bear with me. Just in the meantime, if you can take a look at page 102, just glance at it, read it. I'm going to give you a question now, okay? Bookmark. Let's go. The computer is very slow today. Okay, so while it loads, I don't have patience. On electric engineering, we looked at 4 things. We had power supply, conduction, protection, and control. These are the main 4 things that you have part of an electric circuit. Okay? So that being said, let's see if you guys have your notes and you read them, took a glance at it. What is the battery part of? Which? The battery is part of what? Here, let me write it. You have 4 choices. Okay. Woohoo! The answers are coming down. Power supply, or conduction, or protection, or control. Let's see. Yes, power supply. That was an easy one. Okay, how about copper wire? Let's see. Yes. Yes, very good. How about a switch? Yes, very good. Okay, which is a fuse? Yes, protection. Okay, here's a tricky one. What about rubber around a wire? Actually, I have to change something in your notes. Yeah, insulation. Michael. Okay, there's something you need to change in your notes. I think I mentioned it in class. I don't know who had what. Okay. The rubber wire fits in the insulation only. Okay, let's write this down. Page 102. Rubber wire is only an insulator. So why it's not a protector? Does not protect the entire circuit. In other words, when we talk about protection in here, in this particular concept of electric engineering, we're looking at what can protect an entire electric system. So like the fuses of your house or the breakers of your house. That's what I mean by protection. The rubber wire, although I understand it does protect, but it will not protect if there is a surcharge. Okay, if there's a surcharge, it will still go through. So that's why be careful with this. Rubber wire is an insulator, yes, so that when we come and touch a wire, we don't get electrocuted, but it does not prevent from surcharge. Okay, the breaker and the fuses, the old fuses, are the ones that prevent from overall damage of an entire system. Do you see the difference? Okay, so I had that question too once. On page 102, at the bottom left, you have an image that says rubber around the wire. Write insulator and put a line all the way up to insulator. An arrow. Rubber wire, like I have to change this for next year. This has to be moved up. Okay, up to insulator. The rubber around the wire. They will not protect an entire system. Sounds good? And then you have for some reason, the government feels that you need to know the different types of switches. So let's see if I can find any interesting ones online. Hold on. So like you have the lever type switches, the push buttons, the flip-flops, and the magnetic control. So just recognizing the type of switches they are. Okay. Let's see. Can you guys give me an example of where I would find a push button type of control? You can write an answer on the chat. Where would I find a push button? Let's see, the answer is coming down now. A blender, yeah. That's really good. A doorbell, beautiful. I like the doorbell. Flashlight. Guess it depends on the flashlight. Has to be a push button. Okay, what about, where would I find a lever type switch? A lever type switch. Yeah. The light switch is the most popular one. Yep. Let's see. Here's the question from last year's June exam. Last year's June exam, here we go, right here. Okay. It says, electronic devices contain multiple components with various electrical functions as listed below. Control, protection, power supply, insulation, conduction. And then the question is, which of the following correctly matches each component with its electric function? So I'll give you a minute to look at the questions, the answers. Which of the following correctly matches each component with its electric function? Yes, wonderful. D, the battery is a power supply. The fuse is a protection, not an insulation. Good job for not picking insulation. The switch is the control, and the rubber around the wire is insulation, not protection. So you see, it's good that you didn't pick B, because the rubber was also here written as protection. But remember, protection in the sense of electric engineering is protecting an entire system. Okay, I have like 5 minutes left or 10 minutes left for a quick Kahoot. If you're interested, just stay. I'm gonna post the code right now. If you have another device, I'll give you a minute to go get it. 1 second. Let's get out of this. So this was a pretty good review. What do you say? Yeah. I mean, there's a lot more to it, but we just finished a lot in engineering. This was just reviewing the stuff pre-quarantine. Okay, I just want to cancel this one. So for homework, guys, I recommend that you do the June 2018 exam. I'd like to do an online quiz with you guys next Tuesday on tech stuff. Type, like, I'll have like multiple choice, and then you can answer on a piece of paper, and then we can like do the final. Then this way you'll find out if you're doing good in tech or not. Okay. What do you say? I can either do it this way or put it afterwards. I can put the same quiz on Schoology the same way I did with the chemistry. Sounds good? Okay, done. What's wrong with it? Wait. What's wrong? Oh. All right. And I'm going to share it right now. Here we go. Just a quick little game.